Okay. All right, so guys, let me see what you guys think about this. When I think of a vector field, one of the silliest examples I think of is, do they still have places where when you walk in they have that downdraft? Have you ever been somewhere where you walk in through the door, they have the downdraft? Of course they do that so that it makes like a wall that we can get through, but the air from the outside can't get through.
It's for flies.
Yeah.
They used to have that like refrigerated sections in grocery stores. They had the down, you reach your hand through and you feel the wind coming down. So that's a very, very simple vector field, right? And it would be basically, that everywhere. That's the idea. You could argue it might drop off towards the end or whatever you want to argue about. Let's just look at the middle of it. Right, there it is. So the idea of an integral over a vector field is very simply, I want to add up, one way to look at it is I want to add up how much of the vector field itself follows my curve. So let me see if you guys are with me. So if my curve C was this, that's obviously going to be very positive because it follows. Or if my curve C was that way, it would be just as negative. How are we doing so far? So if I had a curve like this, and of course a curve, I'm sure you understand that, math people, we have straight curves. So if I had a curve like this, what do you think the integral, the type of integral I'm talking about right now, what do you think it would be? Zero, because none of the vector field is aligned with the curve itself. How are we doing so far?
Projection.
Yeah, so it's related to a projection. Related, obviously, more directly to a dot product. Okay. That's not the only way to get a zero, by the way. If I had, for example, a circle in here, would that be positive, negative, or zero? Because on this side it's lined up perfectly, and on this side it's not lined up just as perfectly, right? It's perfectly negative lined up on that side. If I talk about, notice that I have to define an orientation here. So one thing about these different types of integrals, so we just did scalar line integrals, now we're going to do line integrals over vector fields. And that just sounds impressive. If you tell somebody, what'd you do today? Well, line integral over a vector field. What'd you do? So it sounds difficult. And I don't blame you for thinking it's going to be difficult. But it doesn't end up being very difficult. I mean, we just established how to do line integrals along curves in our xy plane, right? So it's going to be very similar to what we just did. It's got to have one little difference, though. This is not a scalar function. This is a vector valued function. So instead of having, let me see, let me go through the steps here. Blah, blah, blah. So I think somebody basically just said it for me. The first type, now another bad thing is there's two types of this. One of them is going to be dealing with the tangential component. That's the type I'm talking about right now. And the other one is going to deal with the orthogonal component. Okay. This is the one that's going to be the flux, and that should make sense. Tangentially is how much of it lies in the same direction as my curve. I'm going to add that up all around that curve. How are we doing so far? So that's why this kind of curve, if I had this as my C2, C2 would be a rather big integral, big positive. This would be a big negative. This would be a zero, because that's positive, that's zero, that's equally negative, so all of it, everything's going to cancel out there. How are we doing? The only difference with this part is it just takes the part that we kind of ignore for the tangential one. And it says, no, then I only want to count it if it's actually perfectly orthogonal, or only count a piece of it if it's a bit of it is orthogonal, just that piece of it that's actually truly orthogonal. How are we doing so far? So at any point on this curve, I've got two main things that are going to help me out to do this. What's this guy going to be? What's that guy right there? Just tangent. So that's the tangent. And what's this guy? Who remembers the normal? Okay, cool. And I understand the grade. I know why you're saying that, but in this case, we really are restricting ourselves to this plane. So that's just going to be the normal to that. Right? And there's a bit of a business to go through to get the normal. But can somebody tell me very quickly, if I have this, what's probably one of the quickest normals to that you can do? Remember, what's got to be true about the normal vector versus the vector itself? What has to be, the dot product must be 0. So what's the quickest way to make a normal? Careful. Well, not using the trivial solution, not using 0 vector. Because the 0 vector is orthogonal and not orthogonal to everything. That's the simplest way, isn't it? Wouldn't that be negative xy plus xy? Or the other simplest way would be that. You with me? And after all the crap they do in the book, they actually come out with one of those, one of them being the correct way because it's pointing in the right direction. So we'll have to figure out which one that is when we get to this time. But it's definitely going to look something like this. So what I really want then is I want to add up all the pieces of this that are in the same direction as this as I move around my curve. And the one reason I don't need a projection is that t, I don't know if you guys remember that t is a unit vector. And this is not really so much a recall as, let me remind you, because it's easy to forget. T was defined to be not just r prime, but r prime divided by the magnitude of r prime. That's t. Cool. How are we doing so far?
So t should have a hat.
Yeah, thank you. Thank you. Forget my little hats and everything. So, what did we figure out before ds was? What was ds? And t now we know is this. So can't we just start plugging it in? So this is what I meant by this. We've already talked about how to do line integrals. We know a lot of the substitutions to make. The one big difference with vector fields, here we are. The one big difference with vector fields is I can't just do a straight up integral. It's got to be somehow a dot product. Thankfully not a cross product, but the other way to do it is going to be a dot product with the normal vector. I can either look at it as picking up all the pieces of the curve that lie in the same direction as the vector field does, or I can look at it as picking up all the pieces that lie perfectly orthogonal to the direction that the vector field does. Those are the two main ways to do this. This is the flux, and this is going to lead to something its own. I'll fill in that blank here in a minute. So if we replace stuff in here, what do we get? We get the integral f dotted with r prime divided by the length of r prime times r prime length dt. So obviously, what happens? Those go away, that kicks ass. So I end up with f dotted with r prime dt.
That's dot product?
Dot product, cool. So if we're working in, there's many different ways to write this integral. If we're working in, I'm kind of debating in my head if I want to show you these other ways to write it. If f is this here, f, g, h. Let me stop right there for a second and make sure you guys are cool with it. F of x, y, z, g of x, y, z, h of x, y, z. It's those three functions, because f is a vector field. It's got to have functional components in there, right? Function-defined components. And r, of course, r prime is what? What vector? What's r itself? R is x, y, z. So what's r prime?
X prime.
x prime of t, y prime, z prime. So another way to write this would be f times x prime plus g y prime plus h z prime. Right, and that's just as clear as that, as I know, until we do a concrete example and see how this works. Depending on the type of problem you're given, it might be better to do this, or it might be better to do this. What is this x prime, by the way? dx dt. I love it. So one more way to write this, just to really blow your minds. If this is dx dt, dy dt, dz dt, dt, don't all the dt's? Oops. Please change colors. All the dt's. I think I have the dt's. Don't all the dt's go away? Yes. dx dt, dy dt, less flourishy. So I have f dx plus g dy plus h dz. Okay. Which again is just as clear as mud. But as we do examples, you'll see that this way sometimes is better to do it, especially when it's defined along like straight lines where maybe x is 0 sometimes and y is 0 sometimes. That would actually be the easier way to do it. This is the way we do it most of the time, right here. Because we have r we can find, and dot products are easy to do. And these are really just the same thing, just written in a different way. So let's do an example. Nobody was hurt. Let's see. This is number 27, I think. Is this the right one I want to do? No, it's not. 35. Oh, what's it say? 35. I don't want to do too much for it here. Oh yeah. Okay, so let me be careful. So this has got to be on the line segment from 1, 1 to 5, 10. So very quickly, everything I just said over here is true for the the two-dimensional problems. You with me? We just take out the z part. It's awesome, right? So that's still true. It's just two-dimensional, not three. So there's a nice example of just a 2D problem. What would r of t be in this case?
1, 1.
That's still step 1. Yeah, it's going to be 1, 1 plus
T.
4, 9. Otherwise known as 1 plus 4t. Beautiful. Now step 2 is normally a good idea to first rewrite f before you find r prime, because one of the biggest mistakes people plug the r prime stuff in. This tells me the points I'm allowed to use. This does. R prime does not tell me the points I'm allowed to use. R prime just tells me the direction I'm going in. So how am I going to rewrite this then? Yeah, 1 plus 9t, 1 plus 4t. Okay, so now we got that rewritten for later. So when I'm able to do that dot product, everything comes out in terms of t. So now I need r prime. And that's amazingly enough 4, 9. So for line segments, it kicks ass. It's just going to be that slope piece, of course. It's a constant thing.
Why did you switch them?
So again,
Why did you switch them on step 2? See the degree?
switch what now? I'm sorry.
1 plus 9t and 1 plus 4t.
Oh, here.
Yeah.
I always, thankfully that step is the same in this one and the last, in the scalar line interval. You've got to rewrite your integrand in terms of t.
But why did you switch the order of?
Oh, just because it's YX.
Oh.
Yeah, yeah.
Okay.
So that's, again, that's that thing I was talking about earlier. Just do whatever the hell this guy says.
Right.
Don't question yourself about that kind of, just say that Y is supposed to go first, and that's where it gets particularly evil. You gotta be careful about whatever it does to you, it switches it around. So this was not bad at all. I mean, the only way to make this worse, the steps were the same, but this came out to be constant. It's not dependent on t. This could be a lot worse, obviously, this step. So how do I set up my integral now? What's the last thing I really need to be able to do my integral? I need f dot r prime. And who can see what that's going to be? What's f dot r prime? What's the beautiful thing about dot product? It's multiply and add, right? So if you get 4 plus 36t plus 9 plus 36t, which is 13 plus 72t. Cool, there's my f dot r prime. That's my integrand now. That's what's inside the integral. But can you see what I mean? A lot of the steps are basically the same, but what do I not need here that I needed before? The magnitude of r prime. So there's little differences, and it's kind of easy to mix when you're doing which one.
What do you integrate with respect to?
So what's my limits going to be in this case?
Start with the limits, that's what I know.
Yeah. So what am I? That's what I forgot on this step. But t is always between what and what if you do the line segment this way? 0 to 1. Okay, cool. Normally, when you do the line segment, it's always going to be 0 to 1. There's almost no need to do some other way. Exactly. So f dot r prime is this. dt. So that is definitely nice.
I can't agree with
If you use a hyperbolic trigonometric, it's no.
Is there such a thing?
Yeah, if you want to.
Can't use a chain.
13t plus 36t squared, 0 to 1. So you get 13 plus 36, 49. 0 is really 0. Cool. Oh, okay. See if I can sneak a little, yeah. Let's do one more maybe. One more that's a little bit more interesting. Let's see what's more interesting there. This might be interesting. 37 looks disgusting. Let's try that one. You guys got all this here? So look at 37 on 986. Oops, it's worse than that. Cool.
What number is it?
Sorry, this is number 37. That looks disgusting as hell, but some of you guys might be able to realize how this piece that looks truly disgusting is going to become very nice.
This goes on the side.
So I'm going to rewrite f. Step 1 is done for me. They give me RT.
Put it to the power of 2.
Now be careful. I kind of, to tell you honestly, I kind of don't like the way they write these. They really should write this under here and this under here inside there, so you don't think that you could actually, it's not a constant, it can't come outside the interval. It actually should be in that vector form. You can always take that, it's the same for both, so that's why they divided it on the bottom. And you guys see how that's a piece of the thing, you have to put it back in. Just a multiple, but it's a multiple that depends on x and y. So it's not a constant.
It can't come out.
But it can come out because it's the same for both of those. I'm dividing that by this. So as x and y change, this becomes what it's supposed to be for each one. But you can't take it outside the integral because it's not a constant. It does change as x and y changes. But the nice thing is, what can I do? What's the second step really? Because I've already got my r at t. Yeah, figure out what f is in terms of the components there, right? So what's this going to be? T squared, 3t squared.
Right.
Yeah, t4 plus
9T4.
9t4 is 10t4, right? Let's clean that up a little bit. We've got t squared, 3t squared over 10 to the 3/2 is whatever the hell it is. It's 10 root 10. Is that cool? It's 1.5 tens. And then t to the 6th. I love it. So one last thing just to make me happy. It's 1 over 10 root 10, which is actually, what would you get? Why do you have to do that? I don't know, I just need to. Root 10 over 100? Oh, screw that, just 1 over 10 root 10. T to the -4. 3 t to the -4. Is that cool? So that's what f is. And of course, you could choose to write it in a different format. It doesn't matter. It's going to come out the same at the end. I'd much rather put things kind of together. So that's step 2. What's step 3 now?
R prime.
Yeah, r prime, and then step 4 is to get ready for the interval. Step 2, step 3. What's r prime? 2t60, I love it. So step 4 is what's f dotted with r prime. It's 1 over 10 root 10. Good, 2t negative 3 plus 18t negative 3, so you get like terms. Oops, sorry guys. Put it that way at the bottom. I'll write it again up here. See everybody back there like,
What the hell is he writing?
so we got, step 3 was this. Our prime of t was 2t, 6t, right? Yeah. And the last step here was f dotted with r prime, which would be, 1 over 10 root 10. 2t dotted with this will be 2t negative 3 plus 18t negative 3. So I end up with 1 over 10 root 10 times 20t negative 3. Or 2 over root 10 t negative 3. Phew. Okay. My golden rule is simplify as much as you can before you have to do the next freaking big thing to it. Right? So simplify that bad boy down. Now you just have to integrate that. And t goes from 1 to 2. Sweet. So basically, if you don't come up with it yourself, you better go back and make sure what the hell it's supposed to do. And again, that's the easy step. I will warn you, in this section, you might get some that require some trig substitution. Not trig substitution, what am I trying to say? Like trig identities, because you might have to integrate cosine squared or something, right? Nothing too evil yet.
Not trick substitution.
Not trig substitution. It's trig identities, yeah. So this is easy, right? 2 over root 10. What do you get when you do the integral? Good. Divided by -2. So those go away. So that's 1 over root 10 negative t negative 2 from 1 to 2, and whatever the hell that is, an ugly ass. Negative 1 over 4 root 10 plus 1 over root 10, and whatever that is. 3 over 4 root 10, I think it is. And you can rationalize that if you really feel like it. All right, so real quick, the last little thing. So we've talked about scalar line integrals. And that was the that type of thing. We talked about, we just talked about there's 2 types of vector field integrals. The first type is this here that we just talked about, the f dotted with r prime. That's not an F. That's not a big F. And the second one is going to be the orthogonal one, the one that leads to something called flux, because it's going to add up all the parts of the vector field that are orthogonal to my curve that I'm walking around on in the xy plane. This one added up all the ones that were in the same direction I was going. This one adds up them all the ones that are normal to the direction I'm going. And that's why it's called flux. Flux kind of sounds like the amount of stuff going through something. At least it does to me, probably, because I got a physics background, because that's what flux is in physics. So I want to real quick talk a little bit about this, and then I'll let you guys out. So we got this here. So for this next type, I have to somehow figure out, I know basically what I want it to be. I want it to be this. And that's basically what we said earlier. I want it to be the part of the vector field that lies along the normal vector, orthogonal to the curve. We all cool with that as a beginning spot? I'm like, yeah, go ahead. All right.
Is that R or
And it's N, sorry, yeah. And of course being the normal vector, normal to that curve at that point. So if I have this here, my tangent vector at a point might be this, my normal would be this. The easiest way to get the normal vector then is to use, let me see if you guys are cool with this. What could I cross t with that would end up giving me n?
something like 0?
Can't cross it with 0.
Right.
What direction am I leaving out when I draw this on this board? Z. And what's the unit vector in the direction of z? Yeah, 0, 0, 1. Is that cool? Okay. So if I do, if I say, and we know this is true, if I cross t with k, which is what that is, that's the ijk, that's k. If I cross those, of course I'm going to get something. Let me see if you guys are cool with this. If I cross this with t, it's got to be this. That's the only thing that could possibly be normal to, or perpendicular to both this guy and this guy. It's got to be here. The minute it's there, oops, that's not 90 degrees. Not 90, it's got to be there. The end. Okay. So if you actually do this, I don't like the way they do this in the book. That's why I'm kind of having trouble thinking about it. Because what does this look like? That looks like a partial derivative or something, right? And they really mean that just to be the x piece of the tangent. Are you cool with that notation? They don't mean x partial derivative, they mean the x piece of the tangent vector. Okay, maybe.
Can you just put X?
We could, why not? So let's just call it our own thing. Let's call it,
XOT.
yeah, I like it, xt, yt. Cool. That makes more sense. Thank you. You stay, that still isn't about screw it. It's a subscript.
Or should it be coupled?
Make it a big T.
Make it a big T? Alright. You guys are very particular. So to get this cross product, I would do this here, right, remember? So I do xt, yt, 0, and then k is 0, 0, 1. Alright, so you did xt, I'm sorry, let me do this in order. So I get yt, I, is that cool?
0.
Yti, xt, j, and be minus, remember that? And of course, for the k, I'd get 0, which makes sense. It can't possibly be in the z direction at all to be orthogonal to something in the z direction. How are we doing there? Semi-decent? I mean, that's nothing major, right? And what does that look like? In fact, I like that all better. Thank you for that suggestion. Remember what I was talking about earlier? To find the normal to xy wasn't one option to make it
Negative.
y negative x,
Right.
right? So then all you have to do, so now I've got my normal vector. Let's write it a little bit, let's write in vector in just component form, yt negative xt.
Is that the case always?
Yes, we just proved it. That's going to be our normal vector for this interval. This has a million different ways to write it also. Let's make this a little less t-ish here. Remember t was r prime over the length of r prime?
Yes.
Which means that the y piece of this is going to be, so this normal vector is now going to be, how can I write this better? Oh, you can do it, Jeff. Y prime negative x prime over the length, yeah, square root of, oh, how do I write that? Oh yeah, duh, just leave it like this. Like that. So
Y, that's Y prime J. Minus H prime.
No, it's Y prime.
Comma.
yeah, it's y I.
Oh, comma negative.
I'm sorry, yeah, exactly.
You just let go of the T's.
Thank you,
Y
thank you.
prime comma.
So, do you remember how we did the interval of f dot t and we just replaced stuff? Because I know what ds is. Now I know what n is, I can dot it with f and put it in there. Right, so now I'm going to have my expression for this thing, which is really called the flux of something. Right? The flux of that curve in that vector field. Really measure of how much of the vector field goes through that at right angles. Yeah.
Why are we doing this?
Why are we doing this? Because I was hoping we all start with an understanding that we want this. This was all trying to figure out what the hell n is, so I can put it in.
Oh, I thought that was
Okay, cool. So then you end up with, at the end of all this stuff, let me just cut to the chase. If you plug this in here, you plug this with the r prime of t, and you can see the r primes are going to cancel out again, like it did before. You end up with, let me see what's the best way to write this. There's several different ways. Now we'll just do that first. And that kind of makes sense because remember f is f of xy and g of xy from doing it in 2 dimensions. And so it'd be f dotted with y prime G dotted with negative x, that's how it ends up there. To me, I'd much rather, to tell you honestly, I'd much rather do this directly, do the f dotted with the y prime negative x prime. I mean, that's just easier to kind of start with, just to do this. This isn't too bad though, obviously, you just do x prime, y prime, multiply it out, but this is just easier for me to remember, whatever's easier to remember. I don't think I'm gonna have, shoot, yeah, I'm out of time. So, obviously the first thing next time is gonna be the quiz, and then we'll do some specific examples of this after we take any questions from homework.
The quiz is just 14.1,
13.5, 14.1.
You don't need exactly.
I can never say no.
I had a general question.
Yeah.